He kōna e purangi tēnei nā te reo irirangi o Aotearoa.
You can have sea ice where you look from underneath, it's absolutely covered with algae. But when we add the platelet ice, we have all of the surfaces of the individual crystals and all of the spaces between them.
So right here, right now, is the platelets that we will first start sampling.
Having this sort of lattice structure there means that you haven't got these fast currents that are there continually sweeping things away. Things can just stay in place and really thrive in that environment.
And everyone, you're like, oh, I'm going to do research in Antarctica, and they're like, oh, the penguins, and you're like, yeah, mate, they're all good, but they're stuffed without these little guys. I'm out here to try and hype up the little charismatic ones so that we can have microalgae on pyjamas one day, maybe,
Kia ora, nau mai haramai. Hello and welcome to the third episode of Voice of the Sea Ice. I'm Claire Kincannon. Last episode, we stepped out onto the sea ice and met some of the researchers interested in the physics of how it grows in the winter and melts and breaks out come summer. Today, we head further out on the land-fast sea ice to a camp set up on McMurdo Sound to learn about life for the scientists living and working on the sea ice, as well as the life to be found within the ice itself.
Seal meat tastes like a good old working horse. And penguin, of course, is just like eating a very, very tough wild swan.
Tom Clissold was the cook on Scott's South Pole expedition from 1910 to 1912. Weddell seals, penguins, Antarctic icefish, these were all part of their meals back then. At Dr. Natalie Robinson's Sea Ice Camp in November 2024, the menu is a little different.
I'm making scones with date, but I decided to use the last of the syrup from the can of peaches, so peach and date scones.
Their camp is a series of modified shipping containers set up on the sea ice, with 6 bright yellow polar tents out in front. One of them is mine for the night. We're in the shipping container that serves as the kitchen, and the smell of scones slowly and distractingly fills the space as Natalie and I chat. But she's not out here for the baking challenge. Remember from last episode that in McMurdo Sound, the sea ice has a few layers. As well as solid ice, there's also the sub-ice platelet layer, a sloshy layer made of big ice crystals that form from supercooled water which float up to stick to the underside of the ice. Natalie and her team are here to study the role that sea ice, and in particular the sub-ice platelet layer, plays in supporting Antarctic life.
It harbours an awful lot of what's called primary productivity, so this is the very base of the food chain. In particular, algae, which you can think of in a terrestrial sense as like the grass meadows, and the concentrations of algae in platelet ice can be many times higher than it is associated with sea ice that doesn't have platelet ice. So it's really a hub for that base of the food chain.
It's quiet and calm in this kitchen right now, but that's because the rest of the team are out working. This is the camp hub, where each day begins with coffee, planning, and a check-in call to Scott Base.
Scott Base, this is K892.
K892, this is Scott Base. Good morning.
Top of the morning to you. I just thought we'd crack into Sked a little early and let you know that everybody is well today over.
This schedule call, or SCED, is a way for the support team at Scott Base to keep an eye on the field teams, and each science project is given their own number. Dr. Jackie Stewart of Victoria University of Wellington will report any incidents from the last 24 hours, update on what the weather is like, and let the base know the team's plans for the day, what they'll be up to and where.
Today we'll be heading out to our B array and we will be getting 3 cores. We'll be doing some light measurements, some conductivity measurements. We will have some people out at Array A finishing the big hole, so it goes all the way through to the ocean. And we'll also be sample processing at camp over.
It's quite the list, but this team is doing big days. Time is short, it's expensive to get here, and the weather is a constant factor. Antarctic storms often eat into science time. When conditions are right, they hustle hard. And if there's anything to say about this team, it's that they have a lot of energy. This is them at 7 a.m.
Activities, 2 core day. 2 core day. A, 2.
3 core day.
Sked done, roles assigned. It's time to get going. We're heading out in the Hagland, a specialised vehicle for driving across the sea ice. They're kind of almost cute. They're a roundy, bright green 2-carriage tracked machine that rumbles easily over the snow and ice surface. This one is also towing a trailer filled with drill equipment. There are 6 of us all together heading out to collect platelet cores, samples of the sub-ice platelet layer that the team will investigate for living critters. We're heading towards the Ross ice shelf, so Ross Island with the Mount Erebus rising up is on our left, and on the opposite side, in the far distance, almost like a mirage, we can see the Victoria coast of the Antarctic continent. Everything is white in between, flat and white. And we're driving to, well, nowhere. I mean, it's a GPS point in the ocean that Dr. Greg Leonard of the University of Otago has marked on a map. And the only thing that makes it different to the other thousands of square kilometres around us is when this ice formed.
Right now, we are in what we've been calling the March ice. So what I did back in the office before I came down this season is I went through those satellite images and I just pretty roughly broke them into categories in terms of when they first formed. And so working from the ice shelf to our east, we have a little band of multi-year ice. So that's ice that actually survived the summer melt season. There's a couple kilometers of that. We are now on the next band, which is formed in March. And then we have another site to our west, which we're calling the May ice. And then go one band further than that, we call the August ice, because that ice has been in there since August. That's where our main camp is and one of our other sampling arrays. And when you go beyond that, that's the ice that's formed since about the middle of August. It's nice and thick and safe to operate on now, but it was not thick enough to put our camp across onto that thinner ice.
He mentions this because their original plan was to have their camp in a different part of McMurdo Sound. But the freezing of the ice didn't happen as expected.
What we're seeing this year is atypical of even 10 or 20 years ago. And what I mean by that is in a typical season, we would expect a larger part of the sound that we're on at the moment to have frozen up earlier in the season at about the same time, and then it would have really thickened continually through that time, and we would expect reasonable consistent ice thicknesses from where we are now, just a few kilometers away from Scott Base, further north into the Sound. But what we've seen over the last number of years now is we're seeing a cycle of winter storms coming through at such a frequency that the strong winds blow out of the south, and if the ice hasn't been in place and thickened long enough, it's not structurally supported enough to resist the wind drag. And it breaks up into pieces and it flushes out to the north and opens up what we call a polynya, which is an open bit of water surrounded by ice. Those events happen from maybe less than a day to 2 or 3 days, and then the cycle kind of resets, and we get our nice cold growing temperatures, ice starts to thicken, but if that repeats within a couple of weeks, the same sort of behavior happens. And we're starting to see that happen later into the season than what we've observed before.
Remember the different layers in the sea ice sandwich that Dr. Inge Smith mentioned in the last episode? So you've got snow on top, then solid columnar ice, then a consolidated solid layer of platelet ice, then the sub-ice platelet layer. Which month the ice first forms affects the thickness of each of these, because, as a rule of thumb, you can expect McMurdo Sound sea ice to grow at about 1 centimetre per day, says Greg. And the longer the ice is around, the more time there is for snow to accumulate on the top and platelet ice to accumulate at the bottom. So one of the first jobs at this site is to figure out how thick the layers they're dealing with are. Greg takes out a handheld drill with a very long bit. He calls them flights. Remember in the last episode Dr. Wolfgang Rack spoke about point measurements of ice thickness? Well, this is how you do it. Lizzy Skelton, a master's student at the University of Canterbury, is helping. She starts getting the measurements of platelet layer and solid ice using a weighted metal bar attached to a measuring tape on one side and string on the other.
So I'm pulling one of these strings, which is breaking through the platelets as we speak, so it has a weight on the end. And now I can just feel that I got through to the ocean, so there's no weight on that rope. And then I pull the other one, And so now the bar has flipped sideways. So when it feels the bottom of the platelet layer, it's going to catch. So here I am now, so I can feel a little bit of resistance. If I pulled harder, I would break through. But right now I've just got a bit of resistance, so I can read that. And that's the bottom of the platelet layer.
So that's 5 meters, 87-ish?
Yeah.
But then we have an offset on the tape, because these tapes, we use them year after year. And there's quite a bit of force involved to pull them up through the ice, and so they break at a regular occurrence. And so we just lop off a bit on the bottom, reset it up, and then we just have an offset that we just include in our notebook.
And so right now I'm pulling really hard and I'm breaking the platelet layer. So the bar is sideways right now, feeling quite dense, so I'm having to pull harder than normal, not hard enough to break the tape.
So you're pulling that metal bar up through the layer of platelets.
I could not pull past the ice, but I can't break the platelets. And you can feel the difference in density of the platelet layer, so sometimes it's really easy, and sometimes you can tell that you're getting to a dense plume.
For her masters, Lizzy has been testing a way to measure sea ice thickness using an electromagnetic device towed off the back of a skidoo. Her results can then be checked against these point measurements and compared with the air-based measurements that Wolfgang takes.
Okay, sea ice,
Ready?
2.44.
2.44 meters.
Yeah.
Thank you.
Lizzy flips the bar vertical and wiggles it back out of the drill hole, so she can do the same thing again twice over. Meanwhile, Greg relays the solid ice thickness result to oceanography technician Ollie Twig, who needs to know for the main drilling to be done.
For solid ice, 2.24. That's nice.
It's showtime, and the team immediately breaks into a well-rehearsed series of steps. All going well, this sub-ice platelet layer coring will take 4 to 5 hours. This is a complicated system that took years to engineer. But it does start with a nice low-tech step, something we could all handle. Once the snow is cleared from the ice, it's drilling time. They make a large hole down through the solid ice, but not all the way through to the water yet. Then, a quick snack, because there's no pausing from the next step onwards. Once they punch through the ice, they run the risk of their equipment freezing in. So the team shifts into high gear. They set up the drill platform with a long core barrel that's going to grab the last bit of the solid sea ice and then the 3 meters of platelet ice below. To keep everything in place, they have to account for the weight of the solid sea ice that they've removed from the top. They do that using fake ice plugs, which make an incredibly satisfying sound as they slide down the core barrel. Once the sample is collected in the barrel, they slowly remove the ice plugs and then use a vacuum-powered gate sampler, which helps them retrieve the platelet layer section by section, which then gets poured into a bucket.
Yummy platelets.
The small section of solid sea ice that they drilled through marks the start of their sampling. Head stuck in the enclosed trailer that's behind the Hagland, Dr. Amy van der Rijs of the University of Auckland and PhD candidate Salvatore Campanile of Victoria University of Wellington are getting it squared away.
Basically, the plug is, I don't know, what do you measure, Sal? About 50 centimeters?
Yeah.
So what we do is we measure the entire thing and we take the bottom 25 centimeters. So we're busy sawing through it, and that will be our first sample.
And quickly, when you took it out, you chucked it under a blanket and into the shade, and that's to keep the light away from it.
Yes, so making sure that it's not affected by the light, which could change the different levels that we're measuring.
They've had problems at this site before, but today, everything went great. There's an efficient pack-up, and then it's back to camp to celebrate with the rest of the team and to get a well-deserved lunch. The samples are placed in the camp's lab to defrost. A large blue shipping container at one end of the line of containers. Amy and Salvatore are already hard at work. It looks very organised for a container lab.
I think it has to be too small a space to be messy.
Climbing into this cosy lab, heated inside, it's one of those times you could forget you're in Antarctica. On the right is a bench with a microscope set up, And beyond that, a black plastic bag has been rigged up to act like a curtain around a series of pumps with different filters. Once the platelet ice samples have melted within the buckets, the processing begins. Amy explains.
We take the water and we will run it through what we call a zooplankton tower. And so it's capturing organisms of different sizes in 3 layers.
Zooplankton is a collective term for a whole bunch of small living things, including krill. They snack on the phytoplankton, the plant-like microalgae.
Thereafter, we take the remaining water that's been filtered through these different size filters, and that's where the filtering starts for a diverse number of different studies.
Dr. Svenja Halfter is interested in the different zooplankton species that show up. Among other things, Salvatore wants to find out if there are microplastics in the samples. Amy herself is using DNA studies to zoom out and get an overview.
My focus is looking at the community composition in a general picture and looking at sort of how it all fits together. There's so much not known about this that it's quite exciting research.
The last biologist in the group is Dr. Jackie Stewart, postdoctoral researcher, surfer, musician, artist, and very much a champion of the little guys.
And everyone, you're like, oh, I'm going to do research in Antarctica. And they're like, oh, the penguins. And you're like, yeah, mate, they're all good. But they're stuffed without these little guys. There's big charismatic things that we like to look at. But I'm out here to try and hype up the little charismatic ones so that we can have microalgae on pyjamas one day, maybe,
Microalgae, or phytoplankton, is where the whole Antarctic food web begins. If you want penguins, and seals, and humpback whales, and orcas, well, you need these teeny tiny single-celled plant-like organisms taking in sunlight and turning it into food. And while you can't see them with the naked eye, under the microscope, they definitely have their own charm.
This is one of the ones that a couple years ago we saw kind of increase in the thinner sea ice. So this is a diatom, which is one of the main types of algae in the communities in the sea ice. And this one in particular is Knitsia stellata. So it's a long, thin microalgae, and they like to kind of group together. And what we're looking at here is kind of a partially formed star that they like to form, where they all join from one end and create this quite beautiful little kind of fan star array, hence the name stellata. But they're very diverse.
Jackie grabs another sample. There's one that looks like a jester's hat, and another that looks like a tiny butterfly. The body a bright green, full of chlorophyll, needed to absorb the sunlight, and the wings a translucent outline.
You can get them in all shapes and sizes, and I think that's one of the things that I underestimated the amazingness of algae for a very long time.
That's no longer the case. Now a true microalgae frother, Jackie has a bunch of questions about how they hold up the big complex food web of Antarctica. The key thing to remember is that different kinds of microalgae make different nutrients that the zooplankton then eat. The zooplankton then in turn get eaten by fish, which get eaten by the penguins, or seals, which get eaten by the orca. You get it.
When you think of a microalgal community, it helps to kind of picture it as the produce section at the supermarket, right? So there are lots of different types of microalgae. They're not just these single cells that all look similar. They're quite diverse, they're quite beautiful, and they all produce different amounts of stuff like proteins and fatty acids, which are things like when you look at the back of a nutrition label, you see monounsaturated fats and things. So it's that type of nutrients that they're producing. So what I'm interested in basically is, what does that produce section look like normally? What's available for things higher in the food web, and how might that change?
Changes to when and how the sea ice forms means changes to snow cover and sea ice thickness, which changes the amount of light that gets through, which changes the microalgae community.
2 years ago, when we had similar ice conditions to what we're seeing now, which were unprecedented at that time, but now we've had, that twice within the space of 3 years. We essentially saw that there were shifts in the main type of microalgae, and there was also less diversity, so less produce available. And that's why we're back here asking that question as to, okay, what does that mean for things that actually that are eating them and that rely on that for survival.
Jackie works out how much algae is in each sample by looking for amounts of chlorophyll. Then she uses DNA to figure out what types of microalgae there are, and then she also looks at the nutrients, the proteins and the lipids that the algae are producing. As well as the different samples from sites with different aged ice, she also has manipulated the snow on top of a patch of ice, scraping some off in one area and piling it up in another to change the amount of light available. Now, to be clear, microalgae don't just live in the ice. They also live in the water. This is the same phytoplankton that sometimes blooms, and you get giant green patches that can be seen from space. But there's evidence that the microalgae living in sea ice and in the platelet ice is particularly important.
The ones that provide the most nutrients for the longest amount of time are the ones in the water column, so you end up with blooms in the spring and things like that. But at certain times a year, especially in the winter, that sea ice and platelet ice microalgal community becomes a lot more important to krill and other critters that grazes on the microalgae, and the ice-associated microalgae can end up being the majority of the nutrients for certain times of year.
And not all microalgae are the same. The water column phytoplankton are used to getting a whole bunch of sunlight. The ones that live in ice are adapted to low light levels. Think of it like running a marathon, says Jackie. Some people are sprinters and will come out hot. Others will push to the front running downhill, or maybe charge uphill. Who's in front will change throughout the race, depending on the conditions.
During the winter, when there's more ice, those microalgae that can live in the low light conditions, they go out into the head of the pack, and the ones that like more light and those kind of water conditions pull back either into the main body or all the way down into kind of being quite hard to find, but they're still there. And then when the conditions are right for them again, they move back forward in that marathon pack and take the lead again. So it's that kind of ebb and flow.
As the sea ice cycle changes, this ebb and flow will change too, as will the nutrients available for the rest of the Antarctic ocean food web, impacting everything from the Antarctic toothfish that's fished commercially here to the iconic emperor penguins and Weddell seals, who also rely on sea ice for habitat.
Emperor penguins are, I think, some of the most badass animals because they go through the most extreme situations that I can possibly think of.
That's next time on Voice of the Sea Ice. But before we finish up, while the food and living conditions might be quite different now to Scott and Tom Clissold's time, some things stay the same.
In the evening, we play cards, play drafts, play chess. Then there was lectures. Various scientists used to lecture on their particular branch of science, Every evening there was a lecture, you see, every evening.
A few days before they left to return to Aotearoa, Dr. Natalie Robinson and her team gave a presentation in the Tati flag, the Barrett Scott base. And it finished up with a song, written and performed by Dr. Jackie Stewart, dedicated microalgae hype woman.
They are teeny, they are tiny, they are red, green and green blue. They're a wandering.
Thanks to Dr. Natalie Robinson and the Platelet Ice sampling team. Dr. Greg Leonard, Lizzy Skelton, Ollie Twigg, Dr. Amy van der Weiss, Salvatore Campanile, Dr. Jackie Stewart, Dr. Svenja Halfter, and Doug Walker.
Oh, phytoplankton, who we should be thanking, making air okay.
Reporting for the series was supported by Antarctica New Zealand, with special thanks to Megan Nichol for her help on the ice and to Anthony Powell for audio recordings. Production help was from Ellen Rikers, editing help by William Ray, Sound design and engineering by William Saunders, with additional sound design by Steve Burridge. Thanks to Nataunga Sound and Vision for RNZ archival audio used in this episode. To see photos of what the Sea Ice Camp looks like and to learn a bit more about the team's work there, you can visit rnz.co.nz/OCW. And if you're enjoying Voice of the Sea Ice, please share it with your friends and family. Tēnā koe I whakarongo mai. Thank you so much for listening. I'm Claire Kincannon. Have a great week. Kia pai te wiki.
They sequester carbon and feed the ocean. Though they are tiny, they are mighty indeed. Oh, they are mighty indeed. One last verse, I swear. So where are they, you wonder, in the vast and open seas? Well, they loiter in the tropics, in the poles and in between. If there's sunlight to be harnessed and some nutrients there, please. They do love some coastal waters or a deep sea upwelling. Oh, phytoplankton, who we should be thanking, making air okay to breathe. They sequester carbon and feed the ocean. Though they are tiny, they are mighty indeed. Oh, they are mighty indeed.